Okay, 4.3 Taylor series. Moving on in Unit 4, which is all about infinite series. So first, let's talk about the road so far. Little homage to the TV show Supernatural. The road so far. Knowing what we know about geometric series and when/how they converge. Infinite geometric series, maybe we should say. Knowing what we know about infinite geometric series and when or how they converge has allowed us to find power series to represent certain functions and functions that are equivalent to certain power series. In this section, we will use a more general technique to construct power series. Little exploration. So this is not so much a typical example that you would see on a test or a homework or a quiz, but more an exploration. Construct a polynomial p of x. So p stands for polynomial, I think. Construct a polynomial p of x that equals a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus a sub 4x to the fourth with the following behavior at x equals 0. So we're going to be figuring out what all these coefficients are supposed to be. You know, like we want this to be the polynomial. It's basically we want to find a fourth order or a fourth degree polynomial that has all of this following behavior. Okay, like it's almost like all of these initial conditions kind of thing. So again, ultimately, we want to figure out what a sub 0 is, a sub 1, a sub 2, a sub 3, and a sub 4. So I think we're going to start with just straight up plugging in 0 to p of x. And that's what we get. So plugging in 0 for all of the x's, right? And all of this is supposed to equal 1, right? So when, see, like p of 0 is supposed to equal 1. So all of this is supposed to equal 1. Well, plugging in 0 wipes out all these terms except for a sub 0. So it turns out that a sub 0 equals 1. So that 1 right there comes right from there. And so next we're going to actually take the derivative, the first derivative of this very general, vague polynomial, and we're going to plug in 0 to that and set it equal to 2, essentially. So think about that for a couple seconds. How are we going to take the first derivative of something like this? Well, I guess you'll just have to pretend in a way that all of these a sub whatever numbers are actual numbers. You know, like for example, this term right here, what if this said like 5x squared? You know, you could take the derivative of that. So once again, the derivative of this would just be nothing. The derivative of this term would just be a sub 1. The derivative of this term, we're going to bring the 2 down and then drop it down to a power of 1. But keep in mind, we're also plugging in 0. The derivative of this term, we're going to bring the 3 down and drop it down to a 2, as well as, you know, we're plugging in 0. And then this term, we're bringing down the 4 and dropping it down to a 3 and plugging in 0. So, gotta love plugging in 0, right? Wipes out all of these terms, and we're left with a sub 1 to equal 2. Okay? Now this is going to continue, you've probably guessed, because now we're going to be taking the second derivative plugging in 0 and then setting equal to 3. So taking the second derivative gets us to here. And then plugging in 0. Alright, see now it's not just a sub 2 that's going to equal, what, 3? But 2a sub 2. Okay. So 2a sub 2 equals 3. And so solving for a sub 2, we get 3/2. Alright, pause the video if you need to finish copying that down, or rewatch it if you need more time for what I've said to sink in. So on the next page, this is something you've already written down from the previous page, and what's next is taking the third derivative. Okay? And taking the third derivative and as well as plugging in 0, we end up with 6a sub 3, and that's supposed to equal 4. And so solving for a sub 3, dividing both sides by 6, you get 4 over 6, or 2/3. And then we got to take the fourth derivative, and that's just going to end up with, this will be gone, and this right here, it'll end up, because this was just got done being 24a sub 4x, and so the derivative of this is just 0, and the derivative of this will be 24a to sub 4. I don't know if I said a to the 4th. If I just said that, I apologize. 24a sub 4, and that's supposed to equal 5, right? And so a sub 4 is going to be equal to 5 over 24. And so when you put everything we found back into this original polynomial of degree 4, right? So we're just kind of now plugging in everything we know to here, and we get this. 1 plus 2x plus 3/2 x squared plus 2/3 x to the third plus 5/24 x to the fourth. And so this was an exploration, and so there was like a punchline, what was the point of doing all of that kind of thing. And so it's very important to notice something, okay? So if you want to take your chances and pause the video and think about what that could be, feel free. But here's what it's very important to notice. The coefficient of the term x to the n, so x to the first, x to the second, x to the third, x to the fourth, this is technically x to the 0, okay? So all of the coefficients, or the coefficient of each term x to the n, is something divided by something. Okay? And it turns out that it's whatever you get by plugging in 0 to the nth derivative, like x to the second power, then it'd be like plugging in 0 to the second derivative. So apparently 3 is what you get when you plug in 0 to the second derivative, divided by n factorial. All of these coefficients, okay, and I know they're simplified now, right? Like 4 over 6, okay, got simplified to 2/3, so it's really hard to see once it's simplified. But all of these coefficients, including this 1 right here and this 2 right here, is p to the nth derivative of 0 divided by n factorial. Okay, maybe this is the best one to see. Okay, when we plugged in 0 to the fourth derivative, we got 5. Okay, and 24 is 4 factorial. 4 times 3 times 2 times 1. Okay, right? When we plug in 0 to the fourth derivative, you're supposed to get 5. And 24 is 4 factorial. So exploration over. Let's kind of, ride that wave into this actual next example, okay? Construct a polynomial, it's another fourth degree polynomial that matches the behavior of the natural log of 1 plus x at x equals 0. Okay, so centered at x equals 0 or at x equals 0, we want to find just a polynomial, okay, with only so many terms, okay, like only to the fourth degree, that kind of models or represents this function at x equals 0. And we just kind of got done doing that, except we were kind of vague about all of this behavior. See, now we want it to kind of behave like this actual function at x equals 0. So we're going to do like kind of the same song and dance, okay? So that is, we want p of 0 to equal the function at x equals 0, and the derivative when we plug in 0 to equal the first derivative at x equals 0, okay, and so on and so forth. So the first thing we're going to do is do p of 0, okay, and that's going to pretty much equal the function, okay, when we plug in 0. Okay, so we're just plugging in 0 to the original function. And the natural log of 1 plus 0, that's just the natural log of 1, which is equal to 0. Okay. Next, we're going to see what's going on with the first derivative. Okay, and so we got to take the first derivative of the function. Okay, so what is the first derivative of the natural log of 1 plus x? Well, it's 1 over 1 plus x. And remember, technically, there's a chain rule, right? We would tack on a chain rule like the derivative of the inside, but that derivative is just, what's the derivative of 1 plus x? It's just 1. So multiplying and tacking on the derivative, multiplying by the derivative of, it's not really going to do anything because it's just 1. So it's just 1 over 1 plus x. Okay, but technically there was a chain rule involved there. Okay, and so when we actually now plug in 0 to that, we get 1. Okay, so far we know that p of 0 equals 0 and the p prime of 0 equals 1. But we have to go all the way to the fourth degree, okay, the fourth power. And so the second derivative, so now we got to take the derivative of that. Now I don't want to, spoiler alert, you get that. When you take the derivative of 1 all over 1 plus x, you get this. And we have to plug in 0, and when we plug in 0 to that, we get negative 1. 0, 1 plus 0, that's squared, yep, negative 1. The third derivative, when we take the derivative of that, we get positive 2 all over the quantity 1 plus x cubed. And when we plug in 0 to that, we get 2. And finally, the fourth derivative. So what's the derivative of that? It's going to be negative 6 all over quantity 1 plus x to the fourth. And then when we plug in 0 to that, we get negative 6. Okay? So let that sink in for a couple seconds. You might be writing this down, but so what we've done is we figured out what p of 0 is supposed to equal, p prime of 0 is supposed to equal, p double prime, okay, yada yada yada. And the actual polynomial is going to be like what we found back here. The coefficient of each term, x to the whatever power, is going to be this divided by this. So what we just got done finding was all of these that we need. Like the 0, the 1, the -1, the 2, and the -6. And now we just have to kind of put all of those coefficients along with whatever factorial. Okay, so, here, technically, I probably should have maybe wrote all this out a little bit more thoroughly, I suppose, on this first example. So if I could somehow call an audible. Ooh, perfect. It's already the right color. What this should have said, okay, if I was writing this out way more thoroughly, this term ends up being 0, of course, but it would have been 0 over 0 factorial times x to the 0, which of course is just 0. Okay, but every term is, your result from the derivative and plugging in 0, all over whatever factorial times x to the whatever. So this term is 1 x to the first, technically, all over 1 factorial. This is x to the second all over 2 factorial with this -1, in the numerator of the coefficient. From the third derivative, we got 2, so we have a 2 right here, x to the third all over 3 factorial. And then the -6 goes here along with x to the fourth over 4 factorial. And that's how you do this, okay? And I already started to clean this up. I mean, like, this should have had a power of 1, really, And I also talked about what this original term is. Again, the original unsimplified term would have been 0x to the 0 all over 0 factorial. Okay? And then when you clean this up even a little bit more, because 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, so 2 over 6 reduces like this, and 4 factorial is 24. And so like -6 over 24, you get -1 over 4. So this would be like, a pretty good cleaned up final answer. Okay? So, some follow-up, some notes. We have just constructed the 4th order Taylor polynomial, okay, for this function at x equals 0. You may recognize it as the first 4 terms of the power series we discovered for the natural log of 1 plus x last section by integrating this geometric series, okay? So we already sort of looked at this series last section. But we could keep going, okay? We could keep going and gradually reconstruct that series 1 term at a time, improving the approximation near x equals 0 with every new term we add. Like we could have went to the 5th power or the 6th power or the 7th power, or we could keep going to like the 50th power or the 1,000,000th power. And we could like, kind of get closer and closer to kind of having the Taylor series, okay, like the infinite Taylor series. All right. Next example. Construct the 7th order Taylor polynomial and the Taylor series. So we're going to see how that works, I guess. But you'll be fine. For sine of x at x equals 0. So the good news is we're still at x equals 0. And plugging in 0 is usually pretty easy. So first we're going to plug it into the original function and get 0. Then we're going to plug it into the derivative. The derivative, of course, is cosine, and we're going to get 1. Then we're going to plug it into the second derivative and get 0 again. Then we're going to plug 0 in. So this 0, we're always plugging 0 into the third derivative. So the third derivative, we end up with negative cosine. And so plugging in 0 gets us negative 1. We got to go to the fourth derivative. And then we got to go to the fifth derivative. And the sixth derivative. What's the derivative of that negative sign? And finally, the seventh derivative. Negative cosine. All right. So now that we have all of those answers, now we can kind of write all of the terms of this polynomial. Remember, there's going to be an x to the 0 term, x to the 1, x to the 2, x to the third, x to the fourth, all the way to x to the 7th. Okay? And all of these numbers, along with the corresponding whatever factorial, are going to be the coefficients of x to the 0 and x to the 1 and x to the 2. So again, I just kind of didn't really write out that this was actually 0 times x to the 0 all over 0 factorial. And this is 1 x to the first all over 1 factorial. And that 0 is there. And this negative 1 is here. And that 0 is there. And that 1 goes there. And 0 and negative 1. All right? That's how we build these Taylor polynomials. Okay? To whatever power, to whatever degree, to whatever order. And so cleaning this up, well, that's a 0, and that's a 0, and that's a 0. So, man. So really, oh, and you could have cleaned this up even more, right? I mean, 3 factorial is 6, and 5 factorial is 120, and I don't even know for sure what 7 factorial is off the top of my head right now. But you could even clean this up even more, right? Now, the series, we have to now pretty much take this pattern, or we want to describe basically like the infinite polynomial. Like if we kept going and added a power 8 term and a power 9 term and a power 10 and just pretty much took it to infinity, how could we describe it with sigma? So there we go. There's a pretty big revelation. We obviously can't write an infinite number of terms. We're going to have to describe using shorthand sigma notation. Okay? So, this final series, first of all, is not every, I mean, we're going to start off with n equals 0 in this case, okay, in this answer. You don't really, I guess you don't have to, but let's, n equals 0. And every single term is not going to end up, well, I kind of lost my train of thought there for a second. Every single term has like x to some power, okay? And in this final answer, we have x to the first power in our first term, and our second term is x to the third, okay? See, it's not like our final answer has x to the 0 as our first term, and then x to the 1, and then x to the 2, and then x to the 3. You know, it does up here, but not in our final series. You know, like if we kept this going, it wouldn't contain every single power. It looks like it's skipping powers, you know, and only having the odd powers, to be frank. You know what I mean? I guess what I'm saying is, behind this box right here is not just an n. You know, we can't describe every single term as just x to the n power, starting with 0 and then 1 and then 2 and then 3 and then 4 and then 5 and then 6, okay? Because it's only really all of the odd powers. So, cutting to the chase, well, you know, again, pause the video if you want to think about how we could just describe only the odd powers, and starting off by plugging in 0 for n, because behind this box is not just an n. So pause the video if you want to think about it yourself, but I'm going to remove the box in 3, 2, 1, 2n plus 1. So if we're starting off by plugging in 0 for n, you know, we're going to end up with the first power, and then when we plug in 1, we'll end up with 3, and then when we plug in 2, we'll end up with 5, and this is how we're only getting the odd powers of x. Okay? What about down here? Okay? What about down here, where we end up going from, like, essentially 1 factorial, and then 3 factorial, and then 5 factorial, and then 7 factorial. Again, we don't end up having every single factorial in our final answer. We're only the odd ones. So to represent that part of it, we have 2n plus 1 quantity factorial. Okay? Now, what else is going on in all of these terms? You know, we don't really end up with an actual coefficient because it was always like 1 or -1, you know, ones really. And I think I just kind of let the cat out of the bag, maybe. The only other thing that we need to represent in our sigma notation is that the coefficients keep alternating from +1 to -1, +1, -1, or it's really just alternating signs, positive, negative, positive, negative, you know what I mean? And do you remember how to represent that and get that happening, and, you know, and represent that sigma wise? Like that. -1 to the n power. Now let's double check here, because, you know, -1 to the n power, or -1 to the n plus 1 power, depending on whether you want to start off positive or negative, or if you're plugging in 0 at the start or 1 at the start. Let's make sure we're starting off with positive and then negative and then positive. So the first thing we're plugging in is 0. Okay, so if we do -1 to the 0 power, that's going to be positive. And then on the second term, we're plugging in 1. So -1 to the 1 power is -1. Okay, so there we go. So there we go. So that was a little bit of a tricksy one to start off with, I suppose, especially with this whole skipping terms, like terms that dropped out. So we only had like the odd powers and the odd factorials. That was a little bit of a tricky dynamic, but, you know, hey. So that would be the answer for the series. You try. So please pause the video and try this one, at least on maybe scrap paper if you're not totally confident. Get some scuzz paper and try this one, you know. But so pause the video, because I'm gonna start removing boxing in a few seconds. So, alright, so hopefully you've tried this one, and we're going to do a Taylor polynomial to the 6th order, 6th degree, for cosine of x at x equals 0. So let's see what happens. Once again, we're still plugging in 0. It's not always going to be that way. Foreshadowing. But we're still going at x equals 0. And so here's what happens with, and we're only going to the 6th degree polynomial. And so we get all of these answers. I'll wait until like the third example to write it all out thoroughly. Interesting. So, right, there's like the 1 and there's the 0. You get the idea, right? So 1 x to the 0 over 0 factorial 0. There's the negative 1, 0, 1, 0, and then negative 1. All right. So once again, with all of these zeros, like we have terms dropping out. Okay. And so we end up with this as a pretty good, actually a much better final answer. Again, like you could have written a more final answer here by like doing the factorials, but it looks like I took this one a little bit more to a final answer. So this was what? This was 2 factorial. So this was the 1 over 0 factorial. 0, this was just 0 factorial. 1 over 0 factorial. And this is 2 factorial, and this is 4 factorial, and this is 6 factorial. Okay? So what would the, it looks like I'm missing the series here, but what would the sigma series look like if we kept these terms going, forever? Okay? So let's see here. Oh, check it out. I can maybe... Oh, that's interesting. Let's make a little bit of room. Yeah. So, actually, let's do this. Just so we don't lose all of that. And let's delete. Just make a little more room. Look at this. A little behind the scenes action. Okay, we already know where all that stuff came from. And so, all right. So, again, starting off with 0. I mean, you can tweak it, I guess, if you wanted to plug in 1 at the start, I guess. But so we want, this is still alternating, right? So does this part still apply? We start off positive and then negative and then positive and then negative. So yep, we want to keep that as just to the n power and not like the n plus 1 power or something. So that works. But now we want the even powers, because this is like x to the 0, right? Remember, and if I haven't said this before, I guess I need to stop and say this now, okay? I've probably mentioned this before, but coming up with the sigma definition is a lot easier, when things are not simplified. Like this term of 1, you got to remember that it started off as like x to the 0 all over 0 factorial. You know what I mean? So this term still has an x to some power all over something factorial, right? So this is like the 0 factorial, 2 factorial. Remember, this 24 is actually 4 factorial, and this 720 is actually 6 factorial. So it's the even factorials and the even powers. You know, this is x to the 0, x to the 2, x to the 4, x to the 6th. So how can we tweak this so that it's the even powers and not the odd powers? I believe, now we'll double check this here in a second, but will that do the trick? Let's see here, because again, we want this to start off as the 0 power and 0 factorial, and then on the next term we want it to be a power of 2 and 2 factorial. So we're starting off by plugging in 0 for our first term. And does that check out? 0 factorial, yeah. And then on the second term, see, this term is when n equals 1. And when n equals 1, yeah, we're good. And remember, this term is when n equals 2, which that'll do it. You know, if we plug in 2 for n, then we got it. So that should be the answer. Okay. Let's generalize what we found and what we've been doing so far with the following definition. So this is just kind of summarizing what we've done. Fk of 0 over k factorial x to the k. Yeah. Yep. Don't need to try to dissect this or explain it. But, you know, write that down, I guess. Pause the video if you have to. Let's do another example. Let's find the fourth order, okay, only the fourth order, Taylor polynomial that approximates y equals cosine of 2x near x equals 0. So we're not even doing the series on this one, right? So the same song and dance, we're going to plug in 0, still plugging in just 0. All right, and then we're going to take the derivative. Ooh, look, we got a chain rule that's kind of out here. And then we take the second derivative. Okay, and the third derivative. Each time the chain rule is kind of like having a times 2, you know. Always times 2, so it's going from, you know, -2 to -4 to +8. And then when we take the derivative of, you know, 8 sine of 2x, there's going to be another chain rule that makes it into a 16 out in front. Okay, so this was just the polynomial. So we're going to put all these numbers, you know, so I guess it's almost like a pop quiz, like have you been following along? Has it been sinking in? You know? So what goes behind this box? You know? 1 from right there. And which makes this x to the what power? 0 power, and what goes behind this box? 0. So this is going to be x to the 1, x to the 2, x to the 3, and x to the 4. So what goes behind this box? That number does, 0. And then what goes behind this box? 1, you know. X to the first power, 1 factorial. X to the second power, what goes behind this box? 2 factorial. What goes behind that box? That -4. Okay? Hopefully you get the idea. Make sure you understand all of this, you know what I mean? So that was a pretty good, like, you know, checkpoint type question, you know, checking to see if you are getting it. And now just maybe cleaning this up a little bit, you know, 0 factorial is just 1. This 0 wipes out this whole term, and this 0 wipes out that whole term, and so when we clean all this up, you know, like 16 over 4 factorial, we end up with 2/3, you know. But there's that example. Okay? All right. What we're going to do next, it looks like, and feel free to copy all this down, I guess, but what we're going to do next is examples that involve plugging in things other than 0. Before we were doing Taylor series generated by the function at x equals 0. Now it could be something other than 0. So what I will point out here is that instead of each term being just x to the 0, x to the 1, x to the second power, x to the third power, it's actually going to be x minus whatever, the quantity to that power. So whatever your a value is, it's going to be x minus that to the 0, x minus that to the first power, x minus that. I mean, technically back here, this was really x minus 0 to the 0 power. Technically, this was x minus 0 to the 1 power, first power, but anyway. So, so this infinite series can be, defined like this, from 0 to infinity, or this just partial sum. If we just wanted a partial sum, like a polynomial, like a 7th order polynomial or a 5th order polynomial, it's only going from 0 to n, you know what I mean? But anyway, go back and pause if you want to copy all that down. But here we go. Find the Taylor series generated by e to the x at x equals 2. Okay? So all it really wants is the Taylor series. But, in order to kind of get an idea of how we're going to define or describe all of the terms of the series shorthand, we're going to generate at least a few terms. Okay, so we're actually going to find at least a few terms of like a Taylor polynomial so that we can describe, the Taylor series. So f of 2 is e to the second. Then we're going to do the first derivative and plug in 2. So what's the derivative of e to the x? Well, it's still just e to the x. And so when we plug in 2, we're going to get e to the second again. And then let's do the second derivative at 2. And we're still going to get e to the second, okay? So the polynomial, okay, because again, the Taylor series is just like the polynomial that goes off to infinity, you know what I mean? But as far as like the 0 power and the first power and the second power, okay, we can at least write those first few terms. Again, so 0 power, it's going to be 0 factorial. First power, 1 factorial. Second power, 2 factorial. Okay, now remember, it's not just x to the 0 power. It's not just x to the 1 power. It's x minus whatever, x minus 2. Okay, it's a really easy thing to forget. So all of these, what the heck? That's supposed to be a 2. I mean, man, there's so much live adjusting I have to do here, but whatever. All right, but remember, whatever you get as your answers also goes in the terms. Okay, so technically, e to the second is that one, e to the second is that one, e to the second is that one. It's always going to be e to the second, which helps. Obviously, we're going to infinity, and I think we're just going to start off with 0 again, okay? But see, every single term is going to have this exact same e to the second. That's actually a very nice thing. Like that this is like an easier type of problem because every single term has just e to the second. Like literally every term. So e to the second is going to be just in our sigma. And then every single term has x minus 2 to some power, starting with 0 and then 1 and then 2 and then, okay? So we're just going to have x minus 2 to the n, you know? Starting with 0 and then 1 and then 2 and then 3 and then 4, it's going to go on forever, you know? And then we also have in the denominators whatever factorial. So it's just n factorial. All right? I hope I didn't under-explain that, you know, the final answer, okay? But let that sink in, you know, pause the video, think about that for a little bit, and make sure you understand that this polynomial is going to go on forever, and that's us describing the series, you know what I mean? But every single term is just going to be this, you know, e to the second times x minus 2 to some power all over that same power factorial, you know? But anyway, moving on, I think we have one more couple of examples, one more set of examples. And we're going to start off by finding the third order Taylor polynomial for this function, starting at x equals 0. Okay, so what's the first thing we're going to do? Well, we're going to plug in 0 to the function, and we're going to get negative 5. And then we're going to take the derivative and plug in 0. First of all, the derivative is what? What's the derivative? That is... And then we're going to plug in 0 and get, I believe, 4. And we want just the third, so we want to go to the third derivative. So first the second derivative, plugging in 0, we get negative 6, and then taking the third derivative, that's just going to be what, 12? And then we're going to plug in 0. So what's this going to be when we plug in 0 to this function? Well, there's really no x to plug into, so it's just going to be 12 again. So let's see. Since it's just really we're going at x equals 0, it's just going to be x to the 0 in that term, x to the 1, x to the 2, x to the 3, and then of course 0 factorial, 1 factorial, 2 factorial, and 3 factorial. So what goes here? What goes here? Negative 5. And so 4, we got 4 here, so 4 goes there from the first derivative. From the second derivative, plugging in 0, we got negative 6. And plugging in 0 to the third derivative, we got 12. Okay? So, cleaning this up, I guess, because there could be some cleanup. 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6. And so cleaning it all up, we just get that. All right? And then the last example, we're doing the same exact function again, but now we're going to see what happens if we're going at x equals 1. So it's like the same derivatives, right? Yeah. But now we're plugging in 1. So what happens when we plug in 1? 2 times 1 cubed minus 3 times 1 squared, blah, blah, blah. Spoiler alert, you get negative 2. And then now we're going to, again, see, now we're going to plug in 1, right? And get 4. When we plug in 1 to the first derivative. When we plug in 1 to the second derivative, we get what? And then when we plug in 1, there's no x to plug in, so it's just going to be 12 again. All right, so again now, one more reminder. When we're doing this at x equals something other than 0, it's going to have to be not just x to the 0, and it's not just x to the 1, it's not just x to the 2, or x to the 3. It's always x minus that to that power, okay? As well as the denominators being, 0 factorial and then 1 factorial, blah, blah, blah. And so what goes here is, what do we get? -2. And then we got 4. And then we got 6. And then we got 12. All right. So this third degree polynomial, man. Whew, well, I'm sure I at least cleaned up. Yeah, geez. I was going to say. So starting the cleanup here, taking the factorials and then dividing into the 6 and the 12 and the 4. I mean, look, this could keep going. Like, this is just going to obviously be x minus 1, and so 4x minus 4, because 1 power. But you're going to have to, like, FOIL this here, like x minus 1 times x minus 1. And then the third power gets even crazier, and then distributing the 2 at the end of it. Wow. So talk about ... I mean, if you wanted to keep cleaning this up and kind of having the final answer being some kind of like standard form. But that's good enough for me, at least for now. But so I mean, that does it for Taylor polynomials and Taylor series, okay? Taylor polynomials, I guess to summarize, the routine is pretty easy to follow, you know what I mean? Doing all these derivatives and plugging in whatever, whether it's 0 or 2 or 3, whatever. I think the tricky part, and the part that maybe hopefully we can follow up on through homework and stuff like that, is coming up with like the sigma representation of the series. Like if they ask for like the full infinite Taylor series, actually representing that using sigma might be the tricky part. But hopefully this is a good start with that. So that does it for section 4.3.